Satellites power your GPS, TV, weather, and some of the internet. So what happens when someone tries to hack the sky? Satellites are not sci-fi artifacts. They're working servers in orbit. They beam navigation, TV, weather, and internet across continents. Yet they run on decades-old cycles with limited power and rarely get physical maintenance. That mismatch, essential services built on hard remote hardware, creates a fragile mix. Today we'll map how attackers reach those services, what defenders build into missions, and why most breaches never require a rocket launch. Thinking 3 layers: space, ground, and user. Space is the satellite and payload. Ground is antennas, mission control, and cloud systems. User is terminals, modems, and customer networks. Those 3 layers connect through radios, IP links, and cloud APIs. A weak password on the ground can cascade to an orbital asset. A misconfigured cloud bucket can leak mission plans. Mapping these layers reveals multiple attack paths and the surprising ease of pivoting between them. You don't need a rocket to attack space. Adversaries hit the easiest target: ground networks and user gear. Phishing, stolen vendor credentials, and unpatched servers are the low-hanging fruit. From there, attackers can reach mission control or jump into telemetry streams. That path is quieter and cheaper than uploading code to a satellite in orbit. So defenders must treat terrestrial systems as the first line of defense, not an afterthought. Space hardware creates 3 security constraints. First, satellites can run for a decade or two, making in-orbit upgrades awkward. Second, radiation-hardened chips are slow and power-limited, so heavy cryptography strains resources. Third, latency and narrow bandwidth limit telemetry and patching. Those limits force designers to prioritize lightweight safeguards and resilient defaults. You can't treat a satellite like a data center. You design for constrained, long missions from day one. Ground stations are attractive targets. Antennas, scheduling systems, and operator consoles connect to corporate networks. A single compromised contractor VPN or weak vendor account can open the mission control door. Networks without microsegmentation let attackers walk sideways into control systems. That's why secure jump hosts, strict vendor access windows, and audited remote sessions are staples of modern ground defenses. Yet many operators still need to harden their perimeter. Radio links bring a different threat set: jamming and spoofing. Jamming overwhelms frequency bands with noise, blocking telemetry and commands. Spoofing forges signals to trick receivers into believing false data. GNSS spoofing can mislead ships or drones by corrupting timing. Defenders use directional antennas, spread spectrum, and authentication to fight this. But RF attacks can be physical, cheap, and noisy, so monitoring the spectrum is as crucial as securing servers. Supply chain risk hides in plain sight. Flight software, FPGA bitstreams, and ground tools pass through many hands and factories. A malicious component inserted before launch can survive in orbit for years. Trusted manufacturing, tamper-evident packaging, and provenance tracking reduce this threat. But the larger the ecosystem, the more touchpoints an attacker can exploit. Securing the supply chain becomes a program-wide discipline, not just an engineering checkbox. Real incidents show how attacks play out. In 2022, a network attack disrupted tens of thousands of satellite modems across Europe, leaving customers dark and hardware unusable. The incident didn't require rewriting satellite firmware. It targeted the ground and user layer to cascade effects. That event taught operators to think about resilience and recovery paths before the outage happens, not after the alarms start ringing. Another case involved a breach into a major research lab's network via a rogue device. Attackers pivoted towards systems supporting missions, showing that asset inventory and network segmentation really matter. A single unmonitored endpoint became the toe that toppled the wall. The lesson is simple: find every device, control its access, and log everything, because visibility is the first step to containment. There are also subtle incidents. Attempts to access Earth observation satellites through overseas ground stations and hardware hacks to consumer terminals all show the range of threats. Some attacks aim to disrupt, others to steal or manipulate data. Each incident shifts focus: protect the command link, protect data integrity, and protect the chain that connects users to orbit. And that variety means defenders must be equally diverse in their tools. Start secure by design. Teams run threat models that map cyber and RF risks across the mission. Security becomes a launch gate alongside power and mass. Frameworks and attack catalogs guide requirements so developers don't bolt on protections later. This saves time and reduces costly retrofits. Design decisions about keys, firmware signing, and network separation begin during requirements, not during integration. Protect the radio link with authenticated commands and encrypted telemetry. Use crypto-agile systems that can switch algorithms if threats evolve. Anti-jam measures include directional antennas, beamforming, and frequency hopping. Protocol hardening closes default configurations that attackers exploit. Together, these controls make it expensive and noisy to attack the link, pushing adversaries back to less reliable paths. Key management deserves its own strategy. Use hardware roots of trust on board and on the ground. Predefine secure rekey procedures that function under degraded comms. Practice rekey operations before launch so teams can recover from suspected compromise. Plan for crypto migration and post-quantum algorithms well in advance. Keys are the crown jewels, and losing them breaks mission trust. Harden the spacecraft, secure boot, signed firmware, and locked debug ports. Partition critical command and telemetry from experimental payloads. Implement lightweight anomaly detection that watches telemetry baselines and triggers safe mode if behavior deviates. Fault-tolerant designs assume partial comms loss and default to conservative, safe actions. These onboard measures reduce the impact of ground compromises and give operators time to respond. Treat your ground operations like a critical data center. Adopt zero-trust identity, multi-factor authentication, and micro-segmentation. Keep TT&C networks isolated from corporate email and cloud apps. Use hardened jump hosts for admin access and rotate credentials after contractor access ends. Basic IT hygiene, patching, EDR, and allow listing matters more than ever when those systems control real hardware in orbit. Secure the supply chain and DevSecOps pipeline. Maintain SBOMs, sign code and containers, and use reproducible builds. Vet manufacturing partners and use tamper-evident packaging for critical components. Integrate static and dynamic testing into CI pipelines and scan infrastructure as code. When a build pipeline is trusted, missions launch with confidence. When it's not, problems can ride into orbit unnoticed. Monitor and rehearse continuously. Telemetry-first monitoring watches antennas, modems, gateways, and onboard signals for anomalies. Run red team exercises that include RF attacks and supply chain scenarios. Build playbooks for jamming, spoofing, unauthorized commands, and terminal compromise. Community sharing of threats and exercises improves collective resilience. Practice makes recovery second nature, not a panicked scramble. Look to the future. Software-defined satellites enable rapid updates yet demand strict code signing and rollback plans. Mega constellations require automated patching and mass key management. Inter-satellite laser links add speed and complexity, expanding trust boundaries. Edge AI on board reduces downlink needs, but introduces model integrity risks. Planning for these technologies now avoids messy retrofits later and keeps defenders a step ahead of attackers. Practical checklist for operators. Start a cyber working group at design. Define rekey and crypto agility before launch. Segment TT&C from payload and enterprise IT. Require secure boot and signed updates, and run an RF-aware red team. For SATCOM customers, harden terminals, change defaults, use unique credentials, and monitor anomalies. For policymakers, require SBOMs, signed firmware, and funded exercises. Early security buys resilience and cheaper fixes than retrofix. Final recap. Space cybersecurity blends tried and true IT controls with mission-specific defenses, authenticated command links, secure boot, key management, segmentation, and relentless monitoring. You can't eliminate risk, but you can make systems fail safely and recover quickly. The North Star is designed for resilience, secure by default, agile in crypto, and practiced in recovery. If you build that way, satellites become a stronger backbone for life on Earth. If this helped you see space security differently, like the video, subscribe for more deep dives, and comment with one defense you'd add to your satellite mission.